Hey guys, welcome back to another video. So in this video, I'll be giving the rundown about thermochemistry, and giving some really basic concepts that will really help us propel throughout the unit. So let's get started. So the first thing I'm going to talk about is energy. Then I'm going to shift into system versus surroundings, and each of these topics have their own small subtopics that I'll go through as well. I'm going to first talk about energy. Right, so energy is super important. It really helps us understand what thermochemistry is. So energy is essentially the capacity to do work. In thermochemistry, we'll be working with reactions like this, where they give off heat or absorb heat in other cases, but in this case, heat is actually like a product. So this reaction gives off heat, so it's exothermic. Something we'll talk about in another video, but the way in which these reactions gain and lose heat is because every molecule wants to be stable. And stability in terms of energy means a lower energy. So every molecule wants to be in a lower energy state. So the reason why we want to study these reactions related to thermochemistry is because we want to quantify this heat and kind of relate it back to this fundamental principle of why do we want a lower energy and how can we achieve this lower energy state. Okay, so now let's talk about essentially what energy is. Now that we've said that it's a capacity to do work, let's relate it to chemistry. So essentially, energy that we know, kind of in a mechanical standpoint. So energy is equal to force over a distance. That really doesn't help us that much in chemistry because, I mean, we know what this is, but it doesn't really help us. So energy can be divided into kinetic energy, and potential energy. Kinetic and potential. And in terms of chemistry, kinetic energy, we really see this a lot in heat. So the more molecules move around or vibrate or just bounce around, that really can be equated to heat. So the more they bounce around, the more heat they give off. So that's essentially what kinetic energy is. 1/2 mv squared. And potential energy, mgh. Potential energy is the energy derived by position. So in potential energy, in terms of chemistry, we really see a lot of this potential energy in the bonds that we have in between atoms. So the stronger the bond, the greater the potential energy. Right? So now let's relate this to the units that we use in energy. So we use the joule. So the joule it's a nanometer. It doesn't really mean much, but it's an SI unit that we use a lot in thermochemistry, just related to energies. And we also use something called the calorie. Notice that this is a small c. And a calorie is essentially the energy required to raise the temperature of 1 gram of water, 1 degrees Celsius more. That's what a calorie is. We're going to be using these units a lot in chemistry, so it's best to understand like what they are, and maybe do a little more research on how they relate to each other. Um, we know now that all of energy can be related by this one statement: energy is conserved. So all of energy um, cannot be destroyed. Like no energy can be destroyed, no energy can be created. It can only change forms. So the way I like to look at this is actually from a physics standpoint. So let's say this is like a cliff, right? And you have like a rock or something like that, and you're dropping it. Okay, you're just it's just going down. Initially, all the energy it'll have here is potential energy, right? MGH. So all the potential energy, all the energy will be potential energy at the top. However, as it accelerates downwards, um, more and more of that potential energy is being converted into kinetic energy. So no new energy is being created. It's just part of that energy is being changed. So now let's talk about system versus surroundings. So system versus surroundings. So these are just two terms for how we label certain regions of thermochemistry. So let's have let's have an example or something where you know let's say like potassium chloride is reacting with um, let's say sodium hydroxide or something, right? So they are in this little beaker of some and I mean Erlenmeyer flags. My bad. And they're reacting. They're in here. This is the system essentially. This reaction mixture is called the system. That's where all the action's happening basically. All the heat's given off. All the heat's taken in. And everything else in the universe is the surroundings. So these are the surroundings. And these two regions, they interact with each other. So as we know, heat is essentially molecular motion. So heat is equal to molecular motion. Notice, guys, heat is actually very different from temperature. Heat is the total molecular motion of certain molecules in a reaction or something. Temperature is the average. So temperature is the average. I mean, they're very similar, but they're also different. So don't get confused by them. They're the average. So back to system versus surroundings. Heat is exchanged between the system and surroundings, right? So let's say you have heat being given off by this reaction. So like once potassium chloride and sodium hydroxide react, heat is given off. And that is actually a negative sign. But let's say heat is introduced from the surroundings into the system. Now that is positive. That's negative, that's positive. So we look at everything from a biased standpoint. We look at everything from the system. So if something's leaving the system, we say that's negative. But if something like heat energy is coming into the system, that's positive. So these two regions are always interacting. And also energy is being conserved. So even though energy is leaving the system, it's always in the surroundings. So the energy of the universe, the system, plus the surroundings will always be the same. It equals the universe. So in the universe, energy is always the same. It's just changing from system to surroundings. It's just moving between these two states. And that's a really important concept to understand. And it will really kind of give us a gateway to understanding the three laws of thermodynamics and how enthalpy, entropy, and free energy, how they all relate to each other. That concludes this video. See you guys in the next one. Have a great day.